So as mentioned, we're going to go through a couple of processes, a couple of commands to check the quality of our RNA-seq reads, to trim the reads, and then to align it to the transcriptome. And we'll be using a bash script to perform all of these tasks. For those who would like to have a look at today's schedule, I'm pasting it in the Zoom chat. I will paste it in Etherpad as well, together with the objectives for today, so that you have an idea. I'll try my best to paste all the code, as we go along, but I might be a little bit slow, so I'll keep up with the code. Before we begin, I would like to very quickly recap the commands that we learned last 2 weeks. You don't have to follow along with me. I'm just gonna quickly show you what we have done. We will use some of this code in a bit, but not all of them. So you're not going to miss out on anything. Just to give a bit of refresher and understanding of what we have done. So we basically interacted with our computer, with our own computer, using a terminal, which I think is very fun because it's a very intimate way of communicating with our devices. We learn commands which can be invoked by typing in a series of code or commands on the terminal. We learn how to print the working directory using PWD. It tells us where exactly the terminal is in our file system, right? We can also change the working directory. We can move to somewhere else in the home directory. Again, the shortcut here, the tilde, is referring to home. We can navigate deeper into the subdirectory, and just by providing the command cd, which is short for change directory. So we can go into here, and now you see that my current directory is now in originals. We can also list the files that we have in this directory. So ls is the function to list files. I like to use the -l flag because -l will give a little bit better list of your files with several other information. So in this directory, there is FastQ folder together with this index file called transcriptome.idx, which I hope you have downloaded it from the, I think I gave it through an email link. So for those who have not, try to do that before the break, because this will be used in the second half of today's session. We can also ls to any other directory that we want, somewhere else in your file system or within this directory that we are in. So I'm going to ls fastq, which is again a directory, and it shows that we have several files in there. And two of the files are the fastq files, which we have downloaded last 2 weeks. So again, for those who have not downloaded, please do so before, actually soon. We're going to use it very soon, and make sure that they are in the gunzip format, that they are compressed in the .gz format. So if you have not, do zip it back to the gunzip, or re-download the two files, whichever is easier for you. We can invoke a manual guide of the functions that we are trying to use. For example, I want to know what does ls do in detail, what other parameters are there. For most computer, you can use man, short for manual, and type the command name. So this will give you a list of helping arguments, helping parameters that you can actually use. For those who are not able to use man, try ls and then --help. This will give some sort of similar helping guide. Might not be the same exact format, but does give you some sort of information on the function. Because some of the code, some of the commands may print out very long lists of lines, we also learn how to clear our screen using the function clear. So I'm going to bring up my terminal a little bit so that you don't get to see code too far towards the bottom. So clear will clear the whole screen and give you a fresh page for you to begin inputting your commands. We also learn how to make directory. So function is mkdir, make directory, and you can follow is followed by the name of the directory that you're trying to make, the test folder as such. So now you see in originals, you see another folder called test folder here. We can also create other things. You can create text files using touch. And then we're going to create a touch followed by the name of the file called test.txt. And this will be saved again in the current working directory. Test.txt is here. We can edit this file using nano. Nano is an inbuilt terminal editor program that you can actually modify the contents of the file. It's currently empty. You can input your information. Here is the README for today, for example. There's several confusions on how to get out from this nano. So I'm going to clarify right now. I'm going to again do it a couple more times later on. I realized the easiest way is actually to first, after you're done with inputting your text, is to type Control O. This applies to all platform, Mac, Windows, or even Ubuntu. Control O will prompt whether or not you want to save this file as the name of the file that has been pre-assigned, so test.txt, and you press enter to tell them yes, save in this file format, and to exit from, after you save and exit from this nano, press Control X and out. All right, we'll do this again a couple more times. So Control O to save, and then Control X to exit. I think this works best for most platform, including Mac. Then we also learn how to move files around. For example, now we want to move, let's say we want to move test.txt into a new folder, into the test folder, for example. Let's start with copy. So copy command is cp. You move test.txt. So what I did earlier on was to autocomplete. So autocomplete allows you to fill up the name of that particular file using the first few characters that you type in. So for example, I just type in TE, I'm gonna just press tab. It gives me autocomplete of test, but because there's a test folder and test.txt, I have to input another character. So now it autocompletes when I press on tab the file that I actually created, and you can move into the folder test folder. Again, tab autocompletes the name of the folder. All right, so that's successful. If ILS test folder as such, you can see that test folder, that in this directory there is this text file called test.txt, which should also contain the same text that we have inputted in nano earlier on. This is copy, so you can copy files here and there. You can also copy folders wherever you want. Then we also have move. Move is special because move actually does two things. Move can rename files and folder. So for example, I'm going to type move followed by test.txt, which is in the current originals folder. And I'm going to rename this into a new name, test new.txt. So I'm renaming the original test.txt to test_new.txt, and this will generate a test_new.txt and basically overwrites the name of the previous file. Then we can then move this file wherever we want, into test folder, for example. And then now in the current folder, there is no file called test_new.txt. It's now found in test folder, which we have moved over in the directory. Right. Then we also learn how to remove or delete the entire directory, which is, again, be very careful when you do this. Command is rm, short for remove. Because this is a directory, you need to provide the /-r, which means recursive. So delete the contents of this folder, including all subdirectories and subfolders and files within the directories. All right. So I'm going to remove the test folder, which I don't need right now. Just remove the entire thing, and you can see that the directory no longer contains this folder. And then we did learn about some commands which we can use to play around with FastQ files. So I'm going to go into FastQ, and I'm going to clear the screen just a little bit. Again, don't worry if you can't follow this. When you don't have to follow this, I'm going to paste this whole code in a bit. We learn how to unzip, which is gunzip. It's with a G because this is a gunzipped compression. Usually you focus on compression, you have zip, which is very common. You have tar. Mac likes to use tar compression. In this case, FastQ uses a gunzip compression, followed by the name of the file that you want to unzip. I'm going to go with the first file, so it takes quite a while to decompress this file. Then you can perform some sort of commands to preview this contents of this file. For example, head followed by srr1. So you can see that no longer you don't have the .gz file in the directory anymore. You have a FastQ file, and you can actually see the first 10 lines by default of this file. You can also count the number of lines in this file. I think this makes more sense to count the number of lines. So to count lines, you have to provide the -l flag followed by the name of the file. And this tells you exactly number of lines in this file. I hope you can see this here. I think number is 1. So it tells you, but there's about 1 million, 10 million lines in these files. And then each of these sequences is sort of grouped as lines of 4, with 4 lines of information, which includes the name of the read, the exact sequence that was obtained from a sequencing machine, and then a separation plus, followed by the quality of the read, of the particular read. We can also sort of do some sort of pattern recognition to find patterns in this file. Function to find pattern is grep, followed by the pattern that you're trying to search for. I'm going to use NNN today, followed by the name of the file that we're going to search this pattern in, and it will give us a list of hits that contains this triple N sequence. Again, you can search for anything you want. You can search for adapter sequence. You can search for example, poly T tail, poly A tails, depending on the orientation that you're trying to search. Another thing, a shortcut, if you want to repeat the code that you have written previously, press on the up arrow key. I'm going to press up arrow key right now. You can see that the previous code appear in history, and I can repeat this and redirect the output into a file. Instead of putting it into terminal, I can put it into a file by typing in this modern sign followed by a name of the file. I think I'm going to put NNN. I think it's going to overwrite. It's fine, I guess. So it will save into this file called nn.txt, which you can see here. I'm going to quickly show you the contents of this file. So you see the hits are all in this file. So this is called redirecting. You can redirect the output to somewhere else. You can also perform multiple other commands followed by grep, which includes counting the number of lines. So I'm going to go up again, up a couple more, and the output of this grep, I would like to count the number of lines, and we can use this pipe, which basically redirects the code from the left-hand side of the pipe into the command on the right-hand side. And I'm going to use WCL to count the number of lines, and it tells you that there are 5 lines or 5 hits in the whole RNA-seq sequence. And again, we can also redirect this output and append, not overwrite, but append the data or in the text file that we created. So I'm going to type it like this. So it means that I'm going to add another line, which basically counts number of lines in the grep output into the file nn.txt. And you can see that if I cat txt, there are 5 lines with sequences, and then a 6th line with the number of sequences from the above output. Right, and last but not least, if you have not done so, we can compress this file again by typing gzip followed by the name of the FastQ file. This will take quite a while to perform. And I think that's about it that we covered last week. So gonna copy this whole set of code into Etherpad, and we can continue on. So I think last week I should have explained a little bit more on paired end sequencing. So I'm going to do it right now and recap a little bit on this RNAseq pipeline before we move on to the first part of the workshop. So on Etherpad, there are two links that have been pasted. Click on the first one to have an idea of how a read looks like. I'm going to share my screen to make sure that everybody can see what's going on. Share. Okay, yeah. Okay, so when you prepare RNA-seq library, basically means a whole pool of sequences that is ready to be sequenced. You typically have a mixture of sequence length because in the preparation steps, you basically shear up your RNA into small bits and pieces and select a desired size, usually within 20 to 200 base pair. You wouldn't sequence anything more than that because the resolution or the efficiency of this SBS or synthesized by sequence technology is limited to at least right now 150 to 200 bases. So you want to pick a sequence within that sort of size, and you will typically flank your sequence with adapter because you need to provide primer sequences to read the sequence of your RNA or CDNA after it has gone through some modification, and ultimately your sequence will look like this. You have your read, your sequence in the middle, followed by a read one adapter and read two adapter. Typically, you will reuse a paired end sequencing using two sets of primers: a forward primer that will read sequence from the 5' end and a reverse primer that reads from the 3' end of your sequence to generate two sets of sequences for each RNA. That is the reason why we have two sequences for one experiment, for one of these sample, and we downloaded both of them at the same time. A lot of these softwares will handle both of these sequences at the same time and process and map and do trimming together. So you don't really have to worry about it because you know that each of the sequences actually comes in a pair. If you do come across with experiments that has that say that it's a single end sequencing, usually it will sequence from either the forward read 1, or read 2. So you have to figure out which primer did they use. Did they use the read 1 primer or the read 2 primer? It doesn't really matter at this point in time because you will still get your sequence read. But later on, when you deal with mapping and you deal with trying to figure out what is the orientation of your sequence, you will need that information on the directionality or the orientation of your sequence. So just keep that in mind. And then when you have these sequences, you can then input your sequence into the pipeline. So I'm going to show you the pipeline again from last week. So we were somewhere around here. So we basically looked at how the output of a sequencing experiment looks like, how the reads look like. It's actually a FASTA file. If you're familiar with FASTA format, it has a name, an ID. Usually, a FASTA file starts with a greater than sign, but this FastQ file uses an @ sign to begin the name of a sequence, followed by the sequence itself and some quality information. We will typically then check the sequence for the quality. Usually, FastQC is the go-to. I've not used FastQ screen and FastX before. FastQC works very, very well. Very intuitive, very fast as well. So we're going to use FastQC today. And then we will then trim the sequences. We check the sequence quality and then trim it. using Trimmomatic. I've used CutAdapt before. It's a little bit slow. It does handle multiple adapter sequences at the same time. So if you have adapter plus some other internal sequence that you want to remove, CutAdapt works very, very well. Trimmomatic does quality-based trimming. So it looks at a certain bin of sequence and determine the quality and trim it accordingly. So I like Trimmomatic as a last pass to make sure that you trim out all those low quality segments of your sequence. So we're going to use Trimmomatic today. We'll run QC again just to check that we get a good sequence after trimming, and then we will do mapping. So this is where the pipeline diverges depending on your project outcome. So today we're going to use a mapping towards this transcriptome using Kallisto. So you're going to use an input, which is an index of the mouse transcriptome. So this is good if you are trying to determine the expression of transcripts in your experiment, and you want to just perform very quickly differential expression of isoforms transcripts between your samples. Because as you can see, after mapping, you will straight proceed to the differential expression using several different tools, and you can perform a functional analysis downstream of that expression analysis. So this is very fast, and Kallisto is what we call as a pseudo mapper because it doesn't require full annealing or full mapping to the transcriptome. It basically looks at these k-mers or small sequences, and it rapidly align your sequences to the transcriptome and figure out what's the probability of this mapping being accurate, and remove those which are not accurate. So you can see later on it's going to be very fast for our purposes. We can also use transcriptome mapping, but instead of approaching in an expression point of view, we can align it using bowtie or BWA to get a idea of where exactly does the read map to visualize at the transcriptome level or genome level, how does the expression of your transcripts look like. So typically you would not immediately get a expression data, you will not get a cow matrix from this, you will get some sort of like an aligned read data that you can actually import into certain programs such as IGV to visualize your read, or upload it to UCSC to see where does the read map to. So this is more for visualization rather than quantification. As you can see, after aligning, you have to provide the output file from the aligner, which is what we call as BAM file, which is binary aligned sequence file, into programs such as RSCM, feature counts to quantify the reads. So you visualize, you're happy with it, you quantify using different tools, and then proceed with differential expression. I typically go in this to this route, to the mapping to the genome, and I've used all three of these sequence softwares in my experience. And the reason is because I'm very much interested in splicing, and in order for you to get an idea of how alternative splicing occurs in your experiment, you have to align to the genome to see how your read basically span across exon-exon junction. This is not as possible using transcriptome mapping because you don't have information on introns. I typically approach my analysis in this format, followed by quantification using RSCM and other tools. So these are different ways for you to, I just realized that you have IGV here. So yes, you can use IGV, UCSC to visualize the BAM files, and then make a decision on the quality and further quantification. So again, you can download all of these tools and softwares if you want to give it a try. It's not necessary for this workshop and for whatever we're trying to do today. But I hope you have the three tools on your computer: FastQC, Trimmomatic, and Kallisto at least, to follow through with today's workshop. again, I hope you get a feel of how the installation works. And some of these tools are easy to install, especially if they are installed on Conda or they're available on Conda. So it's much more easier. Some tools are a bit more difficult because it requires you to build from what we call it source, basically use the raw code and basically install it onto your computer. So if you do face that sort of problem, try to read and follow the code step by step. If not, any point of time, if you have problems with any installation, just let me know and we can troubleshoot any tools that you are trying to install. Okay, so we can start off with our first part of the workshop, which is to check our data for quality. Sharing my screen again. Let me see. Okay, here. Cool. Great. So we will be using a tool called FastQC. I like the name because it's very easy to remember. It's FastQ with a C behind it, stands for QC, quality control. And as with any other programs, any other commands, you can check out the parameters of this tool, the command, using by typing in the name of the tool, in this case FastQC, followed by --help. All right, so it did print out a couple of things. It's quite a long list of description, which is good. But usually when you sort of like read through this help guideline, you will see an idea of how to perform this this command. Basically, what sort of inputs do you require? What sort of outputs would you expect? So in this case, you have to provide FastQC with the sequence file that you're trying to input, and it can be any number of sequence file, which is great. And you can also, I'm not sure if it's mentioned here, you can also provide wildcards. If you remember, wildcards are these asterisks that we actually input to pick out a list of files that follows a certain sort of pattern. So it actually does allow you to use wildcards, which is great. Several arguments that I want you to pay attention to would be this -o, which is an argument to specify the directory that you want to save the output to, and also -t. So -t is somewhere in the middle. I'm going to just scroll. -t is here. So this basically represents the number of threads that you want to perform this operation in. If you have like 1 or 2 files, you don't really need to provide multi-threading. So basically, you provide a couple more CPUs into this operation. If you're on a MacBook or MacBook Pro, you typically have 4 CPUs, which means the maximum number of threads is typically 8. You try not to use more than 7. Actually, 7 will be the maximum that you try to use, and you leave 1 thread for your other operation. If you have other computers, there is a way to actually check how many CPUs you have, and you can use a number of threads accordingly. So if you have 4 CPUs, maximum that you can use is actually 8 threads. It's actually times 2 because it's it comes in well, put it simply, two threads per CPU. So these are the 2 arguments that you want to pay attention to. The rest are fine. You can keep it to the default. You don't really have to worry about it, right? I'm just going to paste this part into Etherpad real quick, and we can proceed. So as mentioned, we're going to run FastQC using scripts. I think this is quite fun because you know, you do not have to retype your code again and again. You can use this script and change several information. You can duplicate this script and use this script again and again for different experiments, different projects, and you know, just with a click of a button or press enter, and the whole script will run for you. So it's like you know, creating a robot and watching the robot do work for you. That's the best thing ever. So we're going to create this script in our script directory. If you created the directory as per we did last 2 weeks, the script directory is in, let me clear the screen first so you can see. So clear the screen, so CD, it's in home, followed by RNAseq, workshop, tab, and scripts. So this should be where the directory for scripts is. For those who have moved your RNAseq workshop somewhere else, or you save it in other directories, you can stick to there. You can stick to wherever RNAseq workshop folder is, but just make sure that in this script and in when we perform any other operations, please make sure that you know exactly the directory to this folder before running the script and everything, right? Alternatively, just copy that folder RNAseq workshop into your home, and that will be much more easier for now. Cool. So we're going to create a script file, and we're going to immediately use nano. We're not going to touch. We can just use type nano to create a new script file, and I'm going to name it run_fastqc, and the extension for a bash script is .sh. So it's short for shell. .sh. If you have a Python script, it's usually .py, and R script is .r, as we have done a month ago. So we're going to type enter, and it creates an empty file in nano, and we can start to type our script. I'm going to start off with this very weird instruction, which is very primitive instruction, but it does have its function right now. Not all programs will use this line, but it's sort of like a norm for people to include this code. So the code is like that. It's a hashtag followed by exclamation mark followed by bin /bin/bash, like this. Okay, it doesn't mean anything. It doesn't invoke anything because it's a hash, so it's a comment. But if you do open up a lot of shell files, it does start with this, and I like to sort of keep it as such, because it might come in handy in the future, right? And then followed by any code, any commands that you want to type, whatever commands that you have learned last 2 weeks, or any command in the future, you can type in anywhere underneath this this opening line. So I'm gonna give an example of a command, a new command, and then we'll see how to run this code in your terminal, right? This shell script in your terminal. The code is echo. So this is like the same as printing out a command into terminal. So echo out a certain text, a certain information into terminal command line. So echo is usually followed by a text. So you can do a open interval commas followed by any text that you want. I'm going to say echo running FastQC analysis, like this. So I'm going to start off the script by printing out what sort of analysis the script is performing, so that you know when you run this script, it has started, there was no errors, and you know the progress of the script. You can echo a couple of times in your script just to see, how does your script progress, where exactly there is a bug or error. It should be quite handy. So let's save this. Again, Control O. Again, even for the Mac, Control O. You will tell you whether you want to overwrite the name of this file. So run_fastqc.sh, press enter, and then it says wrote 3 lines. So you have written 3 lines in this text file, in this shell script. So exit from nano, again, Control X to exit back into your terminal. Okay, so if you want to make sure that, just to make sure that the texts are there, that you have input the right thing, you can do a cat run_fastqc.sh. These are the 3 lines that we have written in the shell script. Okay, simple shell script. We're going to build up in a bit. So I'm just going to test out this script first. So how do you run this shell script after you've created it? Function is bash. So it's just bash script, bash shell script. So function is bash, followed by the name of the shell script as how you typed it, and that's it. Bash followed by a script name. I press enter, and you see that you have echoed out the contents of the script. In this case, the text, a text saying running FastQC analysis, into terminal. We didn't type anything into terminal. We just basically asked bash to run the entire contents of the script into terminal, or perform the whole script. And you can see how this is very useful, because now you can input anything. For example, you can create an entire directory, as what we have created last 2 weeks, using a bash script, and you can create the same directory again and again when you have a new project. So you can run bash on a new shell script to create anything, to perform any sort of operation that you want. And this is something that I really like doing, because when you learn how to create a script and you don't do things repetitively, it changes your perception of work, and just try to make things more efficient again and again. Cool. So we've done this. This is great. So now let's amend the script a little bit more to perform FastQC. So let's go back to nano. So invoke nano and the name of your shell script again, run _ FastQC, again, tab to autocomplete the name, and we are back into nano. Cool. So now go down with your down arrow key, and move your cursor down underneath echo, and we can proceed on with the next set of the code. So let me see. One thing that you have to pay attention to when you're typing script is where is the script in your working directory? Where exactly is this file at, and where is your other FastQ files or other directories relative to your script folder? The reason is the reason why you have to pay attention to this is because if you were to let's say do FastQC and you try to call out the file name just on its own without doing a CD, or without understanding where the files are, you will not get a desired output, because most probably your FastQC file, your FastQ files are not in the script directory, which is currently empty and just contain one script file. So you have to pay attention to the structure of your project, the structure of your files, and change your directory accordingly. For example, now we're in scripts. FastQC files is not in scripts. The FastQ files are in originals and FastQ. Originals followed by FastQ, if you remember the structure. So we have to first change the directory of our working directory to somewhere else, so that we can easily access the files, our input files and output files. So I'm going to change the directory. So I'm going to just basically create a separate line and change the directory to RNA_seq. I'm sorry, you cannot autocomplete this. So you can try as much as you want. You will not autocomplete. So you have to type in very carefully. I will also tell myself that right now. Let me see, it's workshop. Right, and then we're going to change to this directory, and I'll tell you why in a bit. And then the reason is because the FastQ files are in the folder originals, and I want to create a new output, the FastQC output in outputs directory. So I don't want to mix and match, or basically contaminate my originals with outputs from this analysis. So being in this home folder, or this RNAseq workshop folder, gives me the ability to pull out files from originals, at the same time outputting files into output. So that sort of gives me a good, you're in a good position to do anything you want with your files. So I'm going to cd here, and then we're going to first create the output directory. We're going to create with mkdir an output directory in outputs. So I'm going to type it like this, followed by FastQC. Pay attention to the names that you provide to the directory. If it's all caps, make sure that you keep it with all caps when you specify it in the next part. Just make sure that you don't get your files and folders mixed up with the names. Again, I do that all the time. Sometimes you forget the names of the file, so just pay attention to that. right? Press enter so that you can input the next command, and we're going to do FastQC directly, right? FastQC command, and again, if you remember, the input is a list of FastQ files, which can be in a compressed form, and then I'm going to also specify the output directory. So to basically call out all these FastQ files, I'm going to use this command originals, which is where the files are found, /FastQ, and then a wildcard symbol followed by .fastq.gz. So this will call out both pairs or both files of the experiment and perform FastQC and output into the directory that you just created previously. Outputs FastQC. I just made a typo mistake, so make sure that you type in FastQC as how you created in previously. Okay.
For
so just gonna go through. Yes.
I'm not sure if the after original /FastQ, is there a C missing, or is that supposed to be?
No, it's FastQ because this is the directory. It's FastQ.
Okay.
This is the folder that we created last 2 weeks that contains the 2 FastQ files, and the names of this directory is called FastQ.
Okay, that makes sense.
So it's the original file.
Yeah.
And then the output is called FastQC because we are running FastQC, and it sort of makes sense to name it. You can name it anything you want. It doesn't really have the FastQC. Just that I try to keep the naming to the name of the software that I use, so it's easier for you to remember.
Okay.
Okay. So just go on ahead, just to reiterate the code that we have written. We started with echo to just print out what we're trying to run. We change directory from scripts back out into RNAseq_workshop so that we have a control of where the outputs are going to be at and where the original files are. We create a new directory called FastQC in outputs, and then we run FastQC with the input as the 2 FastQ file using wildcard and output it into the directory that we created. And I'm gonna put the cherry on top by echoing completed, just to have this dopamine surge once you see that your script finished. It's nice to have this feeling that it's done. All right, and that's it. Control O to save, and then Control X to return. All right, before I run, just make sure that everybody are in the same page. Just give me a thumbs up if this is fine, if you get the same sort of text as I do. I can cat this again just to make sure that you see the code. Just go and make sure that you are following along with this code. Generally okay. Good. Okay, and then we can start. So run this bash script. So bash followed by run_fastqc.sh and press enter. Ready? Cool. See, this is where even I have problems with. Let me see. So I have an error, or I know why. Okay, so I type in the wrong name of the folder. So it's not original, it's originals. My apologies for that. So this is not originals. If you type in originals with me, chances will be that you also have the same error, and we all had the same error together, right? So save it, Control O, and then Control X, and let's try it again. Happens. I am not a, I'm not perfect in making sure with, oh, sorry, not this, it should be bash. I make this mistake over and over again whenever you start to type in scripts. So as you can see, this is the output from FastQC. It's trying to parse through the 2 FastQ files and tell you exactly the progress of the quality control. And you can actually see, some sort of indication as to which files it's trying to analyze and how many percentage complete has gone through, and then it ends off with your own echo that the QC has been completed. Did everybody get this output, or those who did not get this output, please do sound off. Cool. Okay, cool. So that's done.
I didn't fully, so I think I'm still stuck somewhere.
Sure.
So after typing in bash run fastq .sh, I have, it says command not found. It says line 6 fastq command not found, but it then says completed ... And what was
so basically it's stuck. Is it, did you type FastQC? The command for running FastQC is FastQC. Check if you made a typo at here.
Okay,
1,
there I
2,
go
3,
back to
4,
nano.
4.
Nano.
Yep. So go back to nano.
Yeah. The asterisk in the line, is it superscript?
Which one? This asterisk?
Yeah. Is it superscript?
No, it's shift 8. So there's this this star sign or asterisk sign when you type in shift H. This is again the wildcard that basically picks up any pattern in this directory that ends with fastq.gz.
Okay.
Give it a try. No worries.
Can you copy paste that in the
I did. I already did. So if for those who are having problems with this, you can go to Etherpad and copy the entire code. Again, this is this assumes that your directory is in home. RNAseq_workshop is in home and contains the FastQ files in originals. So if everything is in where it should be, copy this into your shell script and try to run it again.
Can you also overwrite in the nano, or?
Yes, nano works like any editor, so it will overwrite the contents when you save it.
How can I edit?
What about the rest?
How can I edit
rest
something that's already written?
Say it again.
How can I edit? Because I can't seem to edit what is already written. So I have the
are you so do you have the same sort of view as mine?
Yeah.
In Nano? Okay, so when to edit, you can just bring your cursor down, and if you want to delete the whole thing, you can type in, just press backspace and delete the whole thing, and you will just, like any editor, you will clear out the whole screen. I'm pretty sure that there's a shortcut for this, but it's the easiest way to delete the contents. And I'm gonna copy the contents from Etherpad and paste. So on Mac, you can do just a simple Command V to paste into Nano. So I'm going to paste mine, and this is what you get after pasting into the shell script. Okay, you give it a try, Alexis, for a bit. The rest, everything's fine. Give me a thumbs up if you get the same output as me. Okay, cool. So we do get some sort of output from it. So so Alexis, give it a try. I'll take this slow, and then we're gonna go for a break in a bit. So don't worry if you won't miss out too much from here. Okay. Cool. I'm gonna save and then exit. Enter, exit. Okay, cool. So we're done with the shell script. Now let's see how does the output looks like. So if you can remember, we actually create a new output file called FastQC. It outputs. So I'm gonna just quickly ls that file and show you what we have in there. RNA_seq workshop. This followed by outputs, followed by FastQC, like this. All right. You can see they're actually 4 files, sets of 2 files for each experiment. One is a HTML file, the other one is a zip file that contains I'm pretty sure it's a text file of the output that you can actually parse and basically, look at it. There's also some sort of figures in there on the quality control. But today we can go ahead and look at the HTML file. It's easy to open this up and have a look at the data. So if you are on Windows, type in start followed by the name of the file. I'm going to show you the name of the file in a bit. So I'm going to paste this code as well. If you are on Mac, the command is open instead of start. So I'm going to quickly show you. So on a Mac, it's open followed by this, right? The whole entire the path to the HTML file. Workshop, outputs, FastQC, and then let's go with the first one, 731.html. It is quite a mouthful. So if you want to copy it from Etherpad, you can do so. It's already on Etherpad. I'm on Ubuntu, so mine is not open. Again, on the Windows, it's start, right? Start followed by the name of the file, right? On an Ubuntu, it's xdg/open. Okay, I'm going to press enter. You can do this together with me, and you should open up this HTML file in your web browser, whichever default web browser you are actually using, right? I will now change my view to the web browser, which I hope you have successfully done so, to show you the output of the FastQC. Cool. Okay. Right. If you got something as similar to mine, again, give me a thumbs up. Great. Okay, you can go into Finder or your Window Explorer and just double click on the HTML file. Again, we are in this, this workshop to communicate with our terminal. So it's always nice to know that you are able to open up files, HTML files, or even other text files using commands from terminal. And now we can actually now look at the contents of this FastQC file. So you will be greeted with a couple of headers, subheaders. First one contains statistics of your FastQ file name, what sort of sequencer encoding it actually uses, total number of reads from this file, and then some other information on sequence length and GC content. This particular dataset is pretty good. It's very decent. And it doesn't show any of the files, any of the sequences as poor quality. So there's 0 poor quality sequences, which is good. And then you can also see graphs containing information of your reads. So the first metric is per base sequence quality. It tells you the quality or the average quality of your sequence at every base. So this is position 0 or position 1 to position 51 in your read. And for each of the sequences, what is the quality of this base across the entire sequence? And you can see that in this dataset, it's generally quite good. If it's within the green zone above 28, this is pretty good. This is a FRET 33 scoring system. And you can see that generally these are very good quality, although I myself will actually trim this a little bit more just to make sure that I remove this poor noise, this slightly lower quality at the 5' end, but generally this is something that looks very decent. You will see that the standard deviation, the range of this quality is very narrow, and it's all within this green zone. So this is something typical of a good sequencing experiment. You can also look at sequence quality by tile. So instead of looking at per base, look at whether or how the quality is within the lane that you actually sequence, because when you sequence your RNA sequence, it will usually be distributed across the entire lane, and they are annotated based on position or some sort of like ID. So this is by base. In the y-axis, it tells you the exact position of that particular base within the lane, and the color scheme, the heat map, tells you the quality of your read of a particular base. So anything that is blue means that it's very, very high quality. Anything that is slightly green or yellowish means that this is the potential cause of your drop in quality. So this area here within 1001 to 1116 has some sort of poor sequencing calls, and you might want to take a look at it and remove some of the sequence in this region, right? Generally, the rest are quite okay. We can also look at the mean quality of the entire read. And this is exactly the same thing from the first metric, just that instead of looking at by base, this is looking at the entire read. And generally, you see that all of the quality are within the top 3 Phred scores from this graph. By the way, if you see a green tick, it means that this metric is acceptable or can be used for downstream experiment. Then you can also look at the per base sequence quality based on the percentage of the 3 bases. You typically want to see something within this range from 17 to 51, whereby the percentage of A and T is more or less equal. So the green is A percentage, the red is T percentage. So this is more or less equal. GC percentage is in black for G and blue for C. So it's more or less the same. You can see that the first 15 bases are a little bit noisy. Again, due to that drop in sequence quality in that 110, 116 region of the lane. GC percentage is quite good, a good normal distribution around 50%, which is very, very nice. There's very, very low ends, miscalls, although we see a couple of ends previously, but it's like 2 or 3 ends. Generally, you don't see miscalls in your sequence, which is very good. The distribution of length is also fine. All of them are 51 base pair. You don't see truncated sequences, which is not desirable. So this peak at 51 for all sequences is actually good to see. Okay, this is where it starts to a little bit get more technical. So if you look at the blue line, right? The blue line basically tells you what percentage of your sequences are PCR duplicates. This is very common because sometimes when you do your library preparation, you need to get more material to sequence. So you usually run a couple of PCR reactions and sample RNAs or CDNAs from there. And you do expect some degree of duplication. Here, this is very common. This is not due to PCR entirely. This is due to also to repeated sequence in your genome, your transcriptome. All of these sign elements, repeat elements are very abundant. RNA sequences are very abundant. So you do see a certain peak around this, this more than 10 times duplication. But then if you remove this duplication and you look at the red line, you should see a good peak at just a single sequence. So it should peak at 1 and then drop, and you don't see any other duplication occurring more than 2 times. So this is actually a good data set. If you have highly contaminated PCR duplicates, you will see this red line starting to appear a couple more times. That means that your data can be contaminated with PCR duplicates or other sort of duplications. You might want to look at your data a little bit more better and remove your duplicates. Generally, if If it's just solely PCR duplicates, it's fine, because these are also information for you to actually use for quantification. So it's not necessary to remove duplicates, but if it's contamination such as contaminated by bacterial sequences or other highly repetitive sequence, then you might want to clean it up a little bit more. All right, last to metric, this tab that says operated sequences basically tells you the top few sequences which are found again and again in your sequencing, and it actually found this sequence about 7,000 times, 3,000 times, 2,000. I checked this. You can actually input the sequence and copy it into UCSC or BLAST to see where does it map to, because it's not so many sequences. So you can actually do very simple BLAST search. And I think it came from a repeat element from somewhere. I can't remember the name of the gene. Again, you can see it's actually very, easy to kind of get overrepresented repeat element. So we will try to remove this by some sort of quality removal later on. And last but not least, it tells us whether or not there is an adapter contamination in your sequences, and this is good. This is very low adapter content. There are some, as we have seen last 2 weeks, there are some adapter here, but it doesn't make up more than 1% of the entire sequence. So this is actually pretty good quality. Cool. I'm going to paste an example of a batch sequencing experiment, and you can have a look at it during the break or whenever you're free. I'm going to paste this into Etherpad, and I'm going to talk about one last thing before we go for a short break, which is we used Nano to edit the contents of our shell script, which works very well because the encoding of Nano is suitable for most of all the shell scripts, or any scripts is best. If you want to use your own editor, you are, you're free to do so. You can open up in Notepad or I think on Windows there's another, was it Notes or something? You can do so, but please make sure if you run into a problem running the script, the reason is that the encoding of that particular program is not compatible with shell. So this is something you don't see, but in the background, all of your text file has some sort of encoding to it. So that's why I'm using Nano, which is safe for now. You can use, I would recommend you a good text editor that works well with Windows and Mac. It's called Sublime. You can download it if you are doing this more regularly and trying to create scripts. It also has very nice color coding for text to differentiate commands and files and directories and everything. So it's kind of a easy to follow set of code. But basically, what it does is to edit any sort of text file. You open up the text file in a software, double click, and you can type in and amend your text file from there. So in the future, you might want to consider using this. Last 2 weeks, we basically use a set of a bit of commands to download 2 FastQ files from ENA, the repository that holds a lot of this experiment, RNAseq experiment files. And I've shown you using curl how to download 2 of these files given the hyperlink to download these files. The problem is that you wouldn't want to do this again and again for 100 set of files. So there must be a better way to do this. So in Etherpad, I have pasted a segue or like a description for you to download a script that allows you to download this metadata from any or from that particular experiment that we actually looked at. It will download the metadata and run the curl on all, I think there's about 200 FastQ files, 200 pairs FastQ files in the experiment, and download all of them in succession. So don't run it like, right now. Just open it up in your text editor or even in Nano. Just read through the code if you want to have an idea of what sort of code do you need to extract the metadata and how to perform this download automatically without copy paste the entire link to the FastQ file. So this is going to be handy if you want to automate this download process. All right. If you have any questions about this script, let me know. It will work and download all files. I think it's about a couple of maybe 500 gigabytes in total, if I'm not mistaken. So if you don't have 500 gigabytes, please don't download into your computer. Cool. So we have seen the data, the quality control data from our RNA-seq files, and we do have this consensus that it's actually pretty good set of sequences, but we want to do some sort of trimming just to make sure that you get good, better quality reads from there, right? So I'm going to share my screen and then we can move on to the next part. There shouldn't be too much coding from now on. It's just mainly downloading script because writing this script will take quite a while. So I'm going to provide you with the script. You already have the idea of how to write scripts. So it's now going through a script that I've already written, running the script, and then we'll see the output. I guess output here makes more it's more fun to look at the output rather than troubleshooting the script over and over again. Cool. So read trimming, we will use the program called Trimmomatic. It's written in Java, if I'm not mistaken. And if you download it from Conda, or even from the other method that I've shown you, you can invoke the parameters to Trimmomatic by typing in the name Trimmomatic. Right? Type this, followed by, I think -- help should work, Trimmomatic. And you should see a guide on how to use Trimmomatic, right? Trimmomatic comes with another alternative way to download. If you go to their website and see their way of downloading, it is a little bit cumbersome. So using Conda or my method, it works slightly better. There are two options to Trimmomatic that you have to provide, either PE or SE. This refers to whether your sequences are paired end sequences or single end sequences, as what we have gone through earlier today. This is followed by a couple of optional parameters. So let's go to PE, because today we're going to look at PE. By the way, can you see my screen well? Or should I increase the font size a little bit? Give me a thumbs up if it's okay for you. I realize it might be a bit small, so it's fine. It's fine. Okay, cool. So a couple of optional arguments, including threads. We have seen threads previously, so you can specify a number of multi-threads you want to use. You can also specify whether the quality of your, or the quality scale of your sequences is in FRET33 or FRET64. You don't have to provide this. They will actually analyze the scale automatically for you. You can also provide an output to the log file that they will generate together with some sort of summary if you want to look at this sort of data set. Again, I don't usually do this often because they will print out some sort of information here. And for like one or two sequences, you don't really need a whole lot of, and you don't need a new file to look at this output. You can also then use quiet to not print out anything into command line, and the rest shouldn't be so, yeah, the rest is validate pairs, it's not so important here. Okay, the important inputs are this. So you do need to provide the, for pair end, the two input files. So this is the first read followed by the second read as an input. And you also have to provide the output file. So there are two sets of output file for each read. For the forward read, you have to provide the output of the read that passed the trimming. And then you have to provide the output file for those reads which failed the trimming. So they keep all the reads for you, which is good. And then you can actually have the option to use just those reads that pass the trimming step. And you can do this for each of the read pairs. So for read 1, you have a separate name from read 2. We can see an example in a bit. And the last important argument is the trimmer. How do you trim? What sort of like algorithm or style of trimming you want Trimmomatic to actually perform. This is where it gets a little bit complicated because Trimmomatic doesn't do this very well. So I'm just going to quickly show you Trimmomatic help page. You can also follow along. I think I have this here. Yeah, link to Trimmomatic homepage. I'm going to paste this in Etherpad, and I'm going to share my screen as well. Yep, here. Okay. So I'm going to open up a little bit more. So what sort of trimming do they provide? It's going to go down a little bit more. So this is this description of the sort of trimming that they provide, this area here. All right. So you can clip the adapter. The function is Illumina clip. You can cut the adapter sequences from your sequence. You have to provide some sort of information, which actually includes the file that contains all these Illumina sequences and how much match or how much mismatch you want to actually allow between the adapter sequences and your sequences, because it will not be 100%. You can actually provide some sort of confidence of adapter removal to this parameter. You can perform a sliding window trimming, meaning that you can provide a window of sequence, window of size, and it will move from the 5' to 3' and trim out any window that is below a certain quality that you have provided. You can also cut leading and trailing sequences, just cut X number of bases from the start or end. You can also crop the read to a certain length, but this doesn't sound very good, and I don't usually use crop very often because it doesn't specify crop from which side. If you do need to do this, head crop will be better. So in our case, I think we're going to use head crop. We want to remove that first 5 or first 7 bases, which has very poor quality. And then last but not least, I use this very often, which is to remove reads, which after trimming and after doing all your processes, drop read if it's below a certain length. So if it's like below 20 or below 25, you don't really want to use it because it's not going to map accurately onto the transcriptome, onto the genome. So you'd rather drop it rather than use it. Okay, the order by which you specify these inputs will determine the order by which the sequence is trimmed. So if you provide Illumina clip first, it will perform Illumina clip, followed by the downstream parameters. So you can have a look at how it's written. So there's some examples here on how to basically in Illumina clip, you have to write something like this, which includes again the name of the FASTA file that contains your sequences and some sort of indication of the mismatch, and I think this is also the sort of like number of reads, a number of bases that it aligns to and stuff. Might get a bit cryptic, so you would like to kind of like do this several times on several test set sequences just to get an idea of whether you're getting the right trimming or not. Right. Today I'm going to use a script that I prepared beforehand. I'm going to paste the link to the files here. So go ahead. I hope that you are still in scripts directory. So if you are away from script directory, please go back to scripts and download download these 2 files into your script directory. So it's already on Etherpad. So you can copy the entire thing. Do the 2 curl commands. Copy this into your terminal and download it. So I'm going to do that as well. I don't think I have this file. So share screen. Okay. Okay, so I'm here. Just check my scripts directory. Yeah, I don't have these two files, so I'm also going to download it together with you. So just simple paste. I'll paste the first one first. Paste into terminal and enter. It's not a very big file, so you don't have to worry about it. The first is actually a script file that contains the commands for the trimming, and then the other file is the FASTA file that contains the set of sequences from actually adapter sequences from Nextera and TrueSeq. So these are the two platforms that are commonly used to prepare libraries. So I included both into one FASTA file. You can use this in your own experiment because it's actually exhaustive. So you don't have to change or redirect yourself to other adapter sequences. All right, let's have a look at how this script looks like. So cat followed by the name of the script. So it's run_Trimmomatic sh as such. Autocomplete will do this very well. So it starts off again with this optional bin bash line followed by an echo of the analysis that we're trying to do. It will then go back to the RNAseq workshop folder, cd to that folder, and create an output directory as how you have seen previously. I include this -p flag. This is not necessary. It is nice if you are trying to create a new folder that already existed, so it doesn't give you this warning, this error that this has already existed because it's already there. So -p will just make sure that no errors come up if the files and folder already exist. So I'm going to open up this a little bit because it doesn't look so nice here. Okay, better. So followed by Trimmomatic command, again Trimmomatic and PE. This is very important because you have to specify the sort of sequences that you have input. And as you can see, I've input the sequences as such. You see that I have written the arguments in separate lines. You can do so very, very well in bash script. You have to provide this / as terminal to the previous line. So after PE, you have to follow by this / to tell the script that this is a continuation of the entire code. And because of this, you're able to write your arguments in separate lines and it looks a little bit more neater. So second line are the inputs. So the first and the second FastQ file, as you have seen. And we also provide the outputs for the first read. So the name of the trimmed reads is is SRR name of the experiment _1.trimmed.fastq.gz. You can provide the .gz as a extension. It will automatically zip the file. That's very convenient. And then the other output is the unpaired, or basically reads that do not pass the sequencing. So basically, because you are providing a pair of sequences, those which do not pass and those which do not pass in both pairs as a pair will be saved into this unpaired file. So I typically just use the trim.fastq.gz because the number of sequence in here and in the other pair should be the same, and you can provide this as an input to any of the mapping or downstream tools. And do the same thing for the other read. So read 2 will have the same sort of naming, just that replace 1 with 2, and then this is where we will specify the trimming. So you don't have to understand or remember this by heart. You can always change this here again. So Illumina clip, this is the first clipping. So I'm going to remove the Illumina clip or the adapter sequences. I already provided the directory to the FASTA file. I'm going to ask for 2 mismatches. So as long as it's 2 out of, I think it was 2 out of 16 adapter sequence, that should be fine. And then ask for at least a certain degree of alignment, 40 and 15. There's some details on what this means. It can be a bit cryptic what it means by clipping and stuff, but you can try out these values. This is followed by a sliding window quality control. So window of 4 bases. So you will move blocks of 4 sequence and then remove anything that is below 20. Again, this is an average of 4, so 20 is actually pretty lenient, so it's good enough for what we're trying to do. I'm also going to do a head crop of 7 bases. So remove the first 7 and make sure that the entire remaining sequence doesn't drop below 35. This is provided by the min length argument towards the end. Minimally, I would stick to Illumina clip, sliding window, and min length. These are the 3 minimal arguments to a Trimmomatic function. Head crop is not really necessary, but I want to do head crop today because I want to show you that if you do a head crop, you can remove the first 7 bases and you can see how the FastQC output differs, and then we can have a look at how it goes. Cool. So let's run this. Again, type bash followed by the function, the name of the script, run Trimmomatic, and press enter, and you should be able to run Trimmomatic automatically. It will take some time, not too long. This is a single cell RNA-seq data from just one experiment, so it's a very small data set. Within a minute, it should be done on any platform, and we didn't provide any multi-threading option, so this should be rather fast. Let me see if I can paste this to the Etherpad as well while we wait. Right. Trimming of reads are, in my opinion, slightly a little bit more time-consuming as compared to other processes. Not sure why. Maybe the tools that they use are not as optimal as compared to like mapping tools. Sometimes some of my trimming might take overnight just to trim, let's say, 8 pairs of bulk RNA-seq sequences. So do plan ahead if you have a very important experiment or you want to run this analysis, so you know that this might take quite a while. Cut adapt might take a little bit longer, so other tools might take a bit longer, depending on the parameters that you provide. So if you see in your terminal, what it's basically trying to print out here is the options that you have actually input, or the command that you input together with the list of adapter sequences that you have provided in your FASTA file. And it tells you, how many forward reverse sequences are there, and what sort of quality that you're trying to use. So this case is FAT33 quality. So it's done on mine. Give me a thumbs up if yours is also done, just to get an idea of if you are successfully obtained this file. Great. So it tells you in this trimming, 87% of the reads in both files survived the parameters that we have provided, which is good. So we didn't over trim. If you're getting like 50%, 60%, you might want to go back to the parameters, maybe change your Illumina clip parameters, maybe be a bit more lenient if it's too stringent, or even for sliding window. I noticed, based on personal experience, the sliding window can get a bit strict. So if you change this to, like, say 30 and you force a minimum of FAT33 of 30, it removes about 60%, and that's not what you want. You don't want to over remove it, because some of these reads actually are pretty decent. Is that the window that you provide will determine how much is trim, or what's the average quality that you're trying to trim. Out of those, 5% from the reverse read survive, and around 5% also from the forward read also survive, about the same percentage, and then dropped. Number of drop sequences is about 85,000, so about 3% of the sequences are dropped, which is fine. We can work very comfortably with 87% of sequences. This is about still 22 million. So no, it's 2 million. Yeah, 2 million sequences, which is more than enough. Okay. Let's do a little bit of exercise. I know it's about 11:44 right now. It's not going to take too long after this. Run FastQC on this new set of FastQ files. So I pasted the exercise in Etherpad. So basically, there's 3 things that you have to do. One, duplicate the shell file that we have created previously, run fastqc.sh. You can duplicate it, make a new shell script from it, rename. You can again do this in Finder if you want to just copy and paste, or you can rename it using mv command on terminal. Change the script slightly, not too much of changes, so that you now perform FastQC on this new set of FastQ file. If you're not sure where exactly the FastQ file is, you can refer to the contents of the shell file, to the script file, to see where the outputs are, and then run the script so that you get a new set of FastQC output. Right? Shouldn't take too long. I'll give you about three minutes-ish. I will do this together with you as well, but I also haven't have this script ready, so I'm going to do this together on my own. You can try it on your own. Okay, so hope you could give this a try. So on Etherpad, I've pasted the code that I just typed together with you. So you can copy the first one just to make a new a duplicate of the shell file. So CP will duplicate the shell and rename it to run_fastqc_trim. So this is the name of the shell file that I created. You can create your own shell file, that's fine. And make sure that when you do bash and run, you run the right shell script, all right? And then in Nano, open up this newly created file and make sure that you amend the script as such. So everything that I change this. So make a directory instead of FastQC, which is the old directory, add a new name to it, so _trim, just to make sure that now we are doing FastQC on a trimmed set of sequences. Again, you can name it to anything that you want. It will be saved as how you created it. I'm not the best in naming. I can honestly tell you that I'm very bad at naming. I rather just make the file very quickly and then shoot myself in the head and like, why did I name it as such? So you're much more what do you call it, more sensitive or pay attention to names better than me. And then also in FastQC, change the input of FastQC is no longer originals FastQ, it's now outputs trim_FastQ, which is where the output of Trimmomatic is. And it also has this fastq.gz extension, so that's fine. And then output into FastQC_trim that we have created in the line before that. Okay, let's give this a try. Bash followed by run_fastqc_trim. This is the trim run fastqc. Wrong name, trim. Okay, so I'll type enter. You can do the same together with me, and yep, it's running. Again, you see it's running on the trimmed FastQ, not the original FastQ. This is what we want. And the second one is also done. Yeah. So in this case, it also analyzed the unpaired FastQ, which is fine because that directory contains, again, 4 different FastQ files. We are mainly interested in the trimmed FastQ because that's what we're going to use downstream. And very quickly, I'm just going to open up this. I'm just going to do an ls of this directory just to show you here first. ls of RNAseq bookshop outputs FastQ and trim. Just to show you that you see we now have the same 2 sets of files, HTML and zip file, one for each of the 4 files that we created from Trimmomatic. Okay, again, I'm going to paste the way to open up any of this file in Etherpad, so you can copy code for Mac or Windows. For you, I'm going to quickly do this and open up for Ubuntu, xdg open, and open up the FastQ file, the FastQC file. And you can see, sharing my screen. Yep, you can see now the quality gets a little bit better. The sequence length is now no longer 51. Strictly, it has a range of 35 to 44, which is fine. Pretty decent size for mapping. But now this gets a little bit better. You can see much more consistent, high quality sequence. If you go down, these per tile sequences is still not green tick, it's fine because you still do see some spots with poor quality, but generally you don't see very strong area with low quality sequence, so that's, I'm happy with that. Quality scores is still very high. This is still, this is some very irregular GC content in the first few bases, but we did remove quite a bit of it, so this is quite okay. Probably just happening in a very small percentage of sequence, so don't want to spoil the entire read length just because of this set of sequence, and just keep it like that. GC content is now still fine, and content is still as fine. Distribution of length is not as good because you're not getting 51 for all, but hey, we had to trim something, and most of them has at least 35 bases of sequence. That's good enough for mapping. Duplication is fine. As you can see, we also remove overrepresented sequence because we actually impose a quality filtering as well. So this is quite good. Yep. So I'm happy with this. So hope you can appreciate the effects of trimming, what happens after trimming. And then we can now begin with the fun part, which is the mapping part. So similarly, we are going to use a script that I have written. So you can go ahead and copy the link to that script on Etherpad. So this is just one script because Kallisto just requires one script to run with the other inputs as your indices, your index, which I hope you have it in the right folder. if you do have errors in a bit, make sure that your transcriptome.idx is in the originals folder, exactly there, because that's exactly where I specify the input for the indices. Okay, Kallisto, to invoke the function, type in Kallisto, you can do --help if you want. It will tell you these are the arguments to Kallisto. So you should begin with, or basically make sure that you have an index to perform Kallisto. What is an index? So think of an index as a index that you find in a book. So if you want to find a particular word in a book, you can actually refer to this index section that tells you exactly the page that a word is basically found, and it's exactly what it is. So Kallisto built an index of sequences, so short k-mers. I think it's by default, was it 7 or was it 10? So a certain size of sequence, and store the relative position of this sequence in sort of like a dictionary or like an index file. So when you have a sequence of interest that your input that you provide, it will chop out the sequence to this k-mer, so let's say 10, and then match this 10 of your input sequence to your index and figure out where exactly this is in a transcriptome, and then perform some sort of downstream pattern matching to create some sort of accuracy score, confidence score, and there's a high enough confidence for that sequence to be mapped, it will assign that particular sequence that you have input to that transcript, or to that genome or transcriptome. In this case, Kallisto does transcriptome mapping, so to that particular transcriptome. And that's basically it. You do it again and again until you finish mapping the entire list of sequence, and it provides some sort of output in a form of count matrix. So let me see if I can do a help. So that's index. So you can actually build your own index from scratch. You have to provide some files, which I'm not going to go through right now, but if you're interested in making an index on your own, have a look at this command. So you can type Kallisto index to see what other arguments you need to provide to make an index. But to quantify, to map and quantify, you have to provide the quant flag or the quant argument. So this is exactly what you need for quantification. There are two main arguments. You have to provide the index that was created. The index that I actually provide comes from Kallisto themselves. So they made index of the mouse MM10 transcriptome from GenCode, if I'm not mistaken, from GenCode, and package it into an index file for you to use directly with no problem. You also have to provide, again, makes sense, your input files. So if you have a paired sequencing file, you can provide both sequences, both pairs in one, in one command, and it will process both at the same time. And then lastly, provide a output directory, so where exactly you want to save your file into. Okay, several others that you might want to pay attention to will be, again, thread. You can provide threading. As you can see, threading is something that a lot of programs actually do, because they want you to have the option to speed up your processes, so you can provide more threads. You can do bootstrap. So what this does is to repeat the quantification using a bootstrapping method. So you sample sequences and repeat that thing 100 times. Usually people do 100 bootstrap cycles, and make sure that every cycle you get some sort of similar mapping, and they will output for you a sort of HDF5 file that gives you the average quantification based on the bootstrapping that you have performed. This is nice to have, but I'm not going to do this today because it will take some time to sample and bootstrap. So you can try this on your own. It's actually much more accurate than just doing it without bootstrap, as they have actually shown. Other things would be this. You can provide the strandness of your sequence. As I've shown you previously, you have in a pattern sequence, you have forward read and the back and the reverse read. most sequences or Illumina sequences will start off the first read as the reverse read, because when you perform the CDNA reverse transcription, you sequences this read, the reverse read will actually will be read first, followed by the forward read. So it's usually an RF stranded conformation. If you're using other platforms, or you just want to check, what's your strandness, please, you can actually do very simple blast search on your sequence. Just take a few of your read pairs, just take maybe like first 3 of your read pairs and blast, or in UCSC do blood. And you can actually have an idea of which orientation comes first. Is it the R reverse read comes first, or the forward read comes first? You typically don't have to do this, because by default RF stranded will be the default. But if you do have some problems that you see your transcript are not getting enough reads, that you're getting a whole lot of 0 reads from all your transcript, that means that this option is to be supplied, and you can just check your reads are of the right orientation. Again, you're not sure about this, you can let me know if you're having problems in the future to decide the strandness of your data. But for this data that we have, it's a RF stranded, and I've checked. That's about it. That's the usual culprits for this particular command. So I'm going to quickly, show you the contents of this file. Cat of run Kallisto, sh Kallisto. Did I have it wrong? Kallisto SL run. Oh, did I download it? Yeah. Probably I did download it. Thought I did. Okay, I'm gonna download it as well. Cat run Kallisto. Yep. Okay, so it's here. So I forgot to download it, so it's now here, and it's again very simple, similar sort of breakdown. You have first mandatory line, an echo of running the quantification, CD and making new directories, as what we've seen before. We create a new directory called Kallisto. This is where your outputs will be found in. And again, inputs are the index with this sort of argument -i followed by the directory to the index, the output file. As I've shown you, this is the stranded that we're going to go with, because this is how the files are actually oriented. And then last but not least, the 2 FastQ files as an input. All right, simple, very, very simple set of code. Let's run this. Again, it's not going to take too long. So sorry, bash run Kallisto to run this. It's not going to take too long, because it's a single cell RNA-seq data. There's not too many sequences, just 2 million sequence, 2 million pairs, and plan your project accordingly, depending on the scale of your data. If you're going to do this for 100 single cell RNA-seq data sets, make sure that you have enough time and know when the process will be done. Size, storage shouldn't be an issue, because these files are very, very small, megabytes in size. So you don't have to worry too much about having hard disks or external drives to store these files. The only thing is that Kallisto separates out the count matrix for each of the cells. So if you have 100 cells, it will store this count data in 100 different folders. So you might need to find a way to, there is a simple shell script that you can write. Basically, you have to copy all these files in each of these folder into somewhere, or in the parent directory, so that everything sort of like gets consolidated together, and then you can actually import this into R, or sort of combine them to look at the whole thing together. All right. This will be a topic of something in the future. I think I will cover differential expression analysis in the future. So we might take a look at how to import these files and perform expression analysis. But for now, let's look at how this output looks like. And we let's see. We have output somewhere in outputs trim_FastQ. So I'm going to ls there. The RNAseq workshop outputs, and then trimmed_FastQ. So you can see. Oh no, sorry. This is the input. It's Kallisto. Yeah. So this is the output for this sample. So you have 3 files. You have this H5 file or HD5 files. This is like a very efficient file type that stores a lot of information and it's compressed. So if you compare this and this, this is much more smaller in terms of file size, compressed file. Minimally, you would be interested in the TSV file. This is a tab separated format that tells you the quantification. And then this is the run info in JSON file. You don't typically want to open this unless you have the right thing to use Java, if I'm not mistaken, to open up this JSON or other sort of proprietary tools. So I'm going to basically look through the contents of abundance.tsv. You can do this together with me. I'm going to use less and open up this folder, RNAseq _workshop. This is outputs, Kallisto, and then look at abundance.tsv. Okay, don't worry, we are almost there, we're almost done. This is just the last part. I'm just gonna show you how this file looks like, and we can wrap up this whole session. You can practice it on your own free time. All right. So this file has several columns. We have the target ID, which is the name of the transcript. This is the list of transcripts in the mouse transcriptome, the length of the transcript, and sort of the effective length. They sort of break this down to the effective length that they actually normalize and figure out based on the transcriptome. You don't really need to know this, but it might be useful to know which of these columns to use in your differential expression analysis in the future. And then the last 2 columns basically states the estimated counts, number of reads that map to the particular transcript, and the TPM. So TPM is a normalized expression. It stands for transcripts per million, and it means as what it says, which is number of transcripts per million RNA in your sample, right? And you can see that a lot of the RNA or the transcripts has 0 count, 0 TPM, which is very normal for a single cell RNA-seq experiment, because number one, you do not have the same depth as a bulk RNA-seq sequencing. You do expect more, transcript with low expression, no expression at all. You do also have this issue with what is it called? Dropouts. So dropouts basically means that the sampling of your RNA is different for different cells. So you have higher dropout rates, and you don't have all RNAs, all transcripts being sequenced at an equal rate. So it's very common. So you can see now we see this transcript having 13 reads, and this corresponds to about 25 transcripts per million. Okay, you do start to see some data coming up here. So this is exactly what you need for your downstream analysis. So you would typically use the information from the read counts, import it into R, and there are several tools that you can actually use, such as HR or DSEQ, to quantify and compare the expression of your genes or transcripts from this sample to other samples that you are trying to compare. Right, so you see this is another block of transcript which has proper expression, and that's about it. That's about it that I want to show you. And we did get to a very nice ending point here, which is to visually see the output of a mapping algorithm. So if you're gonna go out from less, you're gonna go back to terminal, press Q. Q will exit out from less and go back to terminal, and you can continue on from there. So yeah, so this count matrix is again an input to a lot of other downstream analyses, and I think it's a good stopping point for this workshop. And I do plan to share with you ways to perform differential expression analysis in the future. trying to plan out the contents the next few months. But for now, I think I will stop here, and I want you to, provide some sort of feedback. I'm going to paste this end of lesson feedback for you. So this is a combination of the workshop we did last 2 weeks and today's workshop. So basically, just if you may tell me what is the one thing you learned from this workshop series, and what can be improved on in the future. It's always nice to know, the flaws of particular lecture or workshop, so that future participants can benefit from this, and I learn a lot from teaching and listening to your feedbacks. The last part I added in, last question I added in just a couple of hours ago, which is I plan to do a single-cell RNA-seq analysis next month, just before the summer break. I'm not sure how many of you are interested in this, and I'm also not sure how many of you will be taking a break for the summer. So I just want to have a feel of whether would you be interested in looking at this. It's going to be fun, I tell you. Single-cell RNA-seq analysis is visually more pleasing, because after half an hour of doing it, you will be able to see some sort of like visual outputs that not only looks pleasing, but even if you don't understand it, you feel that you've achieved more than what we have done so far. I certainly did that when I first run this single-cell RNA-seq analysis. Like, the kick you get from just looking at graphs is like fun. So it's gonna be fun. It might take more than 2 hours, probably like 3 hours, aiming for 3, not too long. So might go through QC and all the way to at least UMAP dimensional reduction, at least, so that you can see how the cells actually cluster together. And or maybe even differential expression analysis if you have time. That would be nice as well. So let me know what you think about it. And if not, I wish you have a good rest of the day, and looking forward to see you in the future workshops. Cheers.